Hello again. This is the first real class of the course. The course on the whole will be categorized into three categories, and this is based on the levels of difficulty. There will be a basic level of difficulty, there will be an intermediate, and finally an advanced level of difficulty. Now, the real juicy bits, the things that you hear about in the media, the Higgs boson, symmetry breaking, okay, all of that will be right at the end in the advanced category. So sorry, you will not be able to uh, get to these juicy bits just by looking at the first 3, 4, 5 lectures. Okay, you will have to wait for those, but we'll have to build up to that because those are pretty advanced topics by themselves, and we have to build up to that. We need to get the basics right first. Okay, now for the material of this one video, please refer to the PDF that is attached with this blog post, and that is cl1 underscore l1 dot pdf. That's class 1 underscore lecture 1 dot pdf. So I'll have class 1 lecture 2 dot pdf and so on and so forth. In this first video, I'll not be taxing you guys, so you can just sit back, relax, and listen to me rather than actually have to take notes or anything. You need not take notes in the entire course, but let's just see you want to. In this lecture, I'll not be writing any notes for you, just very elementary introductory lecture. Okay, I'll first tell you a few things about quantum mechanics. Before that, I want to tell you a few things about symmetry, and then we'll directly go and survey the so-called zoo of particles. Okay, remember, particle physics, the whole course, the whole branch of physics is devoted to making sense of what the zoo of particle does. Okay, how they interact with each other, how they interact with themselves even, and various properties. We'll get to know them as the course progresses. The first lecture will be extremely light. Okay, now first let me begin with something called symmetry. Symmetry is something that we probably all know in our daily life. We find some structure very symmetrical. Okay, for example, our body, at least on the outside, is pretty symmetrical. We have two hands, so if you cut the body right from the middle, the two halves will be more or less identical if we look at it from the front, even from the back. The insides of our body are not quite symmetrical because the heart is on one side, the kidneys are one kidney is not exactly aligned, another one is above, one is below, and so on and so forth. But symmetry is very, very important in nature. Okay, for example, let me give you a very nice example of a symmetric figure. Okay, so I have with me a triangle. Okay, this is a simple triangle. Okay, and this triangle is an equilateral triangle which means that the sides are all the same. Okay, the length of the sides are all the same, and the angle is a 60 degree. These angles are 60 degrees. Okay, now if you look at the triangle like this, okay, you hold the triangle like this with this end, this vertex right at the top, and then you rotate it by 120 degrees, you get back the same triangle. You cannot differentiate between this configuration and this configuration. So if I give you this configuration, then you turned away and saw another, so you turned away, and while you were turning away I rotated it by 120 degrees, you will not be able to tell the difference. Okay, now this act of turning it by an angle of 120 degrees, and a very specific angle of 120 degrees, is called a rotation. Okay, it's a rotation by 120 degrees. Okay, this is a transformation. I am transforming the system from this state, and the transformation takes it to another state which is rotated by 120 degrees. Okay, so an example of a transformation is a rotation. In this case, the transformation is a very specific type of rotation, and that is 120 degrees. Since this transformation leaves the system invariant, Okay, in other words, you cannot distinguish between the initial and the final state. It means invariant. The transformation is called a symmetry of the system. So the symmetry of this triangle is a rotation by 120 degrees. Okay, fine. So this system enjoys a symmetry, and that is a rotation by 120 degrees. That's how we are going to put it. Okay. Please note that a rotation by 90 degrees is not a symmetry transformation. Okay, because just brings it somewhere like this. Okay, similarly, a rotation by just 60 degrees is also not a symmetric transformation, because this just becomes this, this just becomes this. Okay, so, and the two states are distinguishable. So a rotation by nothing other than 120 degrees, of course you can rotate multiples of 120 degrees, like this is 120 and this is 240. So if you rotate by 240 degrees or 360 degrees, I would come back to the same state. So 120, 240, 360, 480 and so on, and only those multiples of 120 are rotations, are the symmetries of the system. Okay, take another example. Okay, here I have a hexagon. Okay, the hexagon, this figure can be achieved if I rotate it by 60 degrees. I rotate the hexagon by 60 degrees and I get back the same configuration, and rotate it by another 60 degrees, get back the same configuration. So unlike the triangle, now the rotation by 60 degrees is also a symmetry. The triangle did not have rotation by 60 degrees, a symmetry. Here the rotation by 60 degrees is a symmetry. So the symmetry operation on this is a rotation by 60 degree, 120 degree, 180 degree, 240 degrees, 300 degrees and 360 degrees. So this is the initial position, 60 degree rotation, 120 degree rotation, 180 degree rotation, 240 degree rotation, 300 degree rotation, and we come back to 360 degree rotation. None of these states are distinguishable from one another. So the transformation here is rotation by 60 or 120 etc. of the angles, and that is a symmetry of the system. Okay, we can say similar things about this pentagon. Okay, the pentagon has a rotation symmetry by 72 degrees. Okay, but let's come to a circle. Okay, let's come to a circle. We can generalize this to a sphere, but we'll stick to a circle from now on. The circle has a rotation symmetry by any angle. Okay, I can rotate it by any angle and it will still remain a circle with the same configuration. You cannot say that I've rotated by anything. So you look away and rotate by an arbitrary angle and it's still the same circle. Okay, you cannot distinguish between this and this. It's the same circle. Okay, so a circle enjoys a very special type of symmetry. It's called rotationally invariant, and any angle will do. So if you have a system which, if you rotate it by any angle, the symmetry of the system is such that the system does not change. Okay, it means that the system is invariant under any rotation. That system is called a rotationally invariant system. Okay, so a circle is an example of a rotational invariant system in 2 dimensions. You can draw a circle on a sheet of paper, and the sheet of paper is 2 dimensions. So, and you rotate it by any, angle, and you get the same circle. So, the circle is a rotationally invariant figure. You can extend this from 2 dimensions to 3 dimensions, and when we go to 3 dimensions, it's no longer a circle, it's a sphere, and the sphere is rotationally invariant. Now, in particle physics, we learn that every symmetry of a system, every continuous symmetry of a system.